this one. So 2010 BC1, we have a rate function given to us that is f of t equals 7t e to the cosine t. Oops, that's e to the cosine t. And it tells us that this is our rate of snowfall. It begins at midnight, goes from midnight to 9 a.m. Snowfall accumulates on the driveway at this rate, given in cubic feet per hour, so it is a rate function here. And it says at 6 a.m., Janet starts removing snow at a rate of g of t in cubic feet per hour. And the function that is for the removal part is given by a piecewise function, and it's 0 from time 0 to time 6. It's 125 from 6 to 7, and it's 108 from 7 to 9. Right. So ultimately, again, we have our function of snow going onto the driveway, and this is our function that describes the snow going off the driveway. Okay. And if you had taken this test in 2010, you would notice that this is the same question that was on the AB, so this is also AB1 also. There's no BC stuff in this one. All right. So finally, let's get to the questions here. We got part A. It says how many cubic feet of snow have accumulated on the driveway by 6 a.m. So ultimately, we know that this rate function is our accumulation function, and if it is measured in cubic centimeters per hour, and the graph is cubic centimeters per hour versus hours, then the area under it is going to be just cubic centimeters. So our rate function is going to give us a total here, so our integral should write to be as follows. So from 0 to 6 of f of t dt should give us our result. And again, it's calculator part here, so let's put it in the calculator. You could, this is a reason why it's an AB problem, because if you notice the actual function itself, we had to integrate that. It looks like it's a integration by parts problem, but it's on the calculator part, so you don't need to know integration by parts to be able to do it. So with that, we can go ahead and put in our stuff and go from 0 to 6. And get 142.275. And that would be in cubic feet. I think I said cubic centimeters a minute ago, but cubic feet, sorry. So that many cubic feet have accumulated onto the driveway based on our function. And ultimately, if you got the integral right, it's a point. Another point for time beginning, right? 2 points total for that one. Any questions on part A? All right. And then on part B, we were asked to find the rate of change of the volume of snow on the driveway at 8 a.m. Okay. So the rate of change, keep in mind we're looking for the rate of change of the volume of snow. So at 8 a.m., there's two things that are happening. Okay. If we just wanted the accumulation rate, we would just put our 8 into this function. That would tell us the rate of accumulation. But what's also happening at that point? He's also taking some away. So the difference between those two is going to be our rate of change of volume. So ultimately my f of 8, which is going to be 7 times 8, e to the cosine 8. And then my g of 8, because you got to remember this is the rate at which the snow is falling onto the driveway at 8 a.m. G of 8 is going to be the rate at which the snow is going away from the driveway. She's shoveling it out of there. Okay. And ultimately at 8 o'clock, we know that that rate is constant 108. And again, if we want to find the accumulation minus the removal, then we'll get the rate of change of the snow on the driveway at that particular point. So ultimately we'll do 7 times 8 times e to the cosine 8, and then subtract 108, and we get negative 59.583. Running out of ink here. What would the units be on that? This is our rate of change, right? So it's a rate of change means it's cubic feet per hour. And also, just it doesn't ask us in this particular case, but what would that tell us about what's happening on the driveway then? If that rate is negative. Yeah, there's more going off than going on. She's out doing the storm at that point. Questions on part B? Except for how much is it worth? Only one. All right, let's check out part C here. It says let h of t represent the amount of snow, the total amount in cubic feet that Janet has removed from the driveway at time t hours after midnight, and express h as a piecewise function defined in the domain 0 to 9. So our answer should look like very much like our original here. So for our h function, let's see if we can figure out how much snow, again, has been removed. So keep in mind, does the f function have anything to do with this? No. We don't care how much was on there. We just know how much snow has been removed as a function of time. And again, write it as a piecewise function because ultimately we have our different time frames of what's going on between time 0 and time 6. Ultimately, what's going on between time 0 and time 6? Okay. Keep in mind that at h of 0, how much snow has been removed? At time 0, there's been none removed. And so ultimately, we would remove 0 to 6 of our g of, we don't want to use t here because t is our, actually we'll write it as a function here. Use a dummy variable in here, we don't want to use t again here. So this h of t is going to be this for the first part. And again, this is on time 0 to 6. Which ultimately results in what expression? Okay. If we go 0 to 6 here, if I put a 6 in here, how much snow got removed during that time frame? Yeah, none did. So ultimately, our amount of snow removed during that time frame is none. Okay. All right. Now, we know that our next part here, and when we go from time 6 to time 7, I believe, right? Yeah. So time 6 to time 7. Including on that one. Question is how much snow is removed on that part? Okay, if we go from time 6 to time 7. Well, we can get our same if we go from 6 to t of g of s. And keep in mind that we're writing a piecewise function here. And the reason why we don't put 6 to 7 here is because we're writing a function. Okay? If we wrote 6 to 7 here, we would just get some constant answer again. Okay, the question isn't how much snow has been removed between these times, it's can we write a function so that if we put any time in here, like say we put time 6.5, what if I want to know how much snow was gone at 6:30? Okay? I'd want to be able to put it 6.5 in here then, wouldn't I? Okay? So ultimately we'll write it as a function. Okay? And then for our purposes then, if we were to simplify that, we'd have from 6 to t of 125 ds. All right, and the question is, could we write that? Could we write that as an actual function? Could we write that piece as an actual function? Well, of course, the antiderivative of 125 is 125 s. And if we evaluate that on t and 6, we're going to get 125 t minus 125 times 6. So ultimately it'd be 125 times t minus 6. Alright. So for that particular part, think about why this would make common sense too for, just like I said, just from what we know. We know that from time 0 to 6 she's removed no snow whatsoever. We know that from time 6 to 7, so between 6 and 7, she's removing at a rate of 125 cubic feet per hour, a constant rate. Okay. Why t minus 6 here though? Because ultimately if I want to put 630 in there, okay, if I just had t in here, then that would be 125 times 6.5, wouldn't it? But she's not taking any snow out of there for those first 6 hours, is she? So ultimately she's taking it out at that rate, and if I put a 6.5 in here, that would just give me a half. So it'd be a half hour at a 125 rate, and that would make sense in our context, wouldn't it? Okay. So you can do it with the integral, or you can think of it that way also, but ultimately this equation is going to go with our times 6 to times 7.
So you can make that the integral?
It doesn't say it gives both, so I'm not sure. I don't know if there was notes on this one. I didn't see any notes on it, so I'm not sure if you can leave it as the integral or not. I guess the fact that it just says let h of t represent the total amount of snow, express h as a piecewise defined function. I mean, this, if you write it as an integral with 6 and t, then that's a function. So I would guess that that's going to be okay. Like I said, I didn't see. I'll remind me after we get done here. I want to look at the student samples and see if somebody left it like that and still got the points. So we could probably maybe figure it out if somebody did that. Okay. But I would think, like I said, that qualifies as a function right there. So I would think that would be okay to just leave it as such. Okay. If they didn't want it as an integral, I guess they would say, because there's been other questions where it says write it as a function not involving an integral or something like that. So I would say that'd be okay. And then the other part here, we need to make sure that we handle the other part correctly by doing the third part, which was from 7 to, was it 9? So from 7 to 9, our function is going to be similar, except for it's going to be from 7 to t of g sub s, or g of s ds. However, remember this function needs to give the amount of snow that's been removed. So for that first hour, how much did we remove? We removed 125 in the first hour. Okay, so it'd be 125 plus 7 to t. And ultimately that would give us our result. If you want to do the same thing you did with this one, winds up if you do the 120, 108, this is 108, so it'd be 108s. So it'd be 125 plus 108 would be t minus 7. Because ultimately after the 7th hour, then you'd be working in that other rate. Okay. So that would be your expression without the integral. And either way, we're 3 points. Each part's worth the point. So if you got essentially the 0 function here for this one, okay, got a point. If you had the integral or the simplified version, point for that, and then point for the bottom one. You got to make sure you have the 125 here because you've already accumulated 125, and the function needs to be the total accumulation at that point. We have 125 plus the integral from 7 to t of g of s. So 3 total there. All right, questions? All right, well, let's take a look at part D then. In part D, it says how many cubic feet of snow are on the driveway at 9 a.m.? Well, we know that the integral from 0 to 9 of f of t is going to give us the total amount of accumulation that we have from the storm, right? We also know that the integral from 0 to 9 of our g of t function is going to give us how much has been removed. Okay. So if we can find both of those, should be in good shape. So let's see what happens. We know that our f of t function is calculator. So we go from 0 to 9 this time. Our f function, get 367.335. All right, and we also know that from 0 to 6 on this is going to be 0. We know from 0 to 7 it's going to be 125. And we just wrote the function a minute ago. It's going to be that from 7 to 9 in this case of our g of s function. Now again, do you have to use calculus necessarily for this part? From 7 to 9 it's a constant rate, isn't it? Just going to be another 108, 108. Okay. So ultimately if we do 125 plus 216 would be the result from that. So 108 for 2 hours straight. So that would be 341. So minus 341. Give us our final answer if we do those two subtracted. So we get 26.335 feet cubed. So in other words, she's still got a little work to do, huh? All right, here's a breakdown for that one. The three parts, three points here. One for the integral here. So if you got the accumulation part. One for figuring out the h of 9. So if you figured out the amount, the 341, I guess, which ultimately would be that, I guess. And then the final answer. Did the subtraction correctly. Answer point. Good to go. All right. Questions on part D? Okay, well, let's take a look at number 2. So, we got done this time. We have a function that is time as the independent variable. E of t is entries. This is going to be a one-day contest to name a new baby elephant at the zoo. And the visitors get to put entries in the special box from time 0, which is noon, to time 8, which is 8 p.m. And the number of entries in the box, t hours after noon, is modeled by the differentiable function e from time 0 to time 8. And the values of e of t are in hundreds of entries, keep that in mind, at various times throughout the table. So in other words, reading that table at time 0, there's no entries. Time 2, which is 2 p.m., there's 400 entries, and 1,300 and so on. So got a lot of people who really care about this baby elephant, huh? 2,300 at the end. All right, so in part A, the question is use the data in the table to approximate the rate in hundreds of entries per hour at which entries were being deposited into the box at time 6. So at time 6, we have 2 points in our graph. We have 5, 13, and then we have 7, 21, this being t and this being e. And if we want to know the rate of change at time 6, we could just find the what of these 2 points. Let's find the slope. So 21 minus 13, 7 minus 5. Oh, I lied. Yeah, no, I did it right. And we'd ultimately get 8 over 4. No, 8 over 2, thank you. Which would be 4. And keep in mind that translates to 400 because these are in hundreds of entries per hour. So it would be 400 entries per hour would be the final. So again, we're adding the zeros because the units here are in hundreds of entries per hour. And ultimately that was worth 1 point. You got that approximate slope. Questions on part A? All right, part B then. Says use the trapezoidal sum with 4 subintervals given by the table to approximate 1/8 times 0 to 8, or times the integral from 0 to 8 of e of t dt. And as soon as we see that kind of integral, we should automatically have average value in our mind. That's an average value problem. Okay? So this is the average, and again, keep in mind that e is the number of entries in the box. So this is going to be the average number of entries. We'll write it down in a minute, but this is ultimately the average number of entries in the box at any time between time 0 and 8. And so the work itself, we have non-uniform subintervals there. We go from 0 to 2, then 2 to 5, 5 to 7, and 7 to 8. So if we have non-uniform subintervals, we have to apply our trapezoidal rule as follows. We got 0, 0, we got 2, 4, we got 5, 13, we got 7, 21, we got 8, 23. Bottom line is we connect the dots between the points and draw our trapezoids as such. And then take each of those parts, this one, this one, this one, this one, all 4 of those, and just find the areas of each of those individually. So you'll notice that this one's not actually even a trapezoid, this one's just a triangle, as it turns out. So if we do 1/2 times base times height, do the I'm going to always treat the horizontal lengths as the heights. So the height of my triangle here would be from 0 to 2, that's 2. And base, if you will, is this, which is that 4. And so therefore we get 4 for that one. The next one, that base goes from 2 to 5, that makes 3. And then the two bases from the chart are 4 and 13. So we go 4 plus 13. That would be that trapezoid. So we get 17 times 3 is 51. Times a half would be 25 and a half. Next one goes from 5 to 7, that's 2. The heights are 13 and 21, or the bases if you will. And of course that's 1, and so adding these two together we get 34. Be the area of that one. And the last one goes from 7 to 8, so that's only 1 in the height direction, and then the two bases are 21 and 23. 21 plus 23 is 44. 44 times a half would be 22. And so if we add all those up, and keep in mind this is a calculator problem, so you don't actually have to do all that by hand, even though it's just pretty simple arithmetic for the most part. But if we add that all up, we get 4 plus 25.5 plus 34 plus 22. And keep in mind though that that's just the integral part. We need to multiply that by the 1/8 to get our average value. So we get 10.688 would be the numerical answer here. And then the explanation part says using correct units explain the meaning of this in terms of the number of entries. And again, we'd say this is the average number of entries. So average number of entries in the box between time 0 and time 8. And it's the average number of entries in the box in what units? Maybe hundreds of entries. So that would be our units part right there. Alright, point breakdown. If you got the trapezoidal sum correct, you got these numbers, okay. Got a point for that. If you got the approximation, if you took that and multiplied it by 1/8, you got this 10.688. If you got that, that's another point. So 1 point for that, 1 point for the trapezoidal sum, and then 1 point for the meaning. So if you got the meaning correct, then you're good to go. This was AB also, yeah. What's that? Yeah, because we've done it before together. Yeah, practice one. Yep, you're right. Alright. Okay, let's move on to part C if we're good to go there. So part C says that we want to find, it says at 8 p.m. the volunteers begin to process the entries. They process the entries at a rate modeled by the function p. So this p function is t cubed minus 30t squared plus 298t minus 976. And that's also in hundreds of entries per hour. According to the model, how many entries had not yet been processed by midnight? Well, how many have been processed would be the integral from 8 to 12 of p of t dt, wouldn't it? Again, this is our rate function in entries, hundreds of entries per hour. So if we integrate that, we're going to get hundreds of entries. So if we do that, let's see what we get here. And again, we can do this by hand, but there's no good reason to if it's a calculator problem. X cubed minus 30 x squared plus 298 x minus 976. And we get 24,336. I get, I'm going to type it in wrong. Oh, you're right, there we go. Let's try that again. So minus 30x squared. Oh, that makes a lot of difference there, doesn't it? Okay, so we get 16. And ultimately that's how many have been processed. How many were in there at the beginning at 8 o'clock? There's 23. Keep in mind both of these are in hundreds, so when we get down here with the answer being 7, would actually be how many are left? 700 entries left to be dealt with. Alright. And from there, we are good. 700 entries would be how many are left to be done. 2 points there, one for the integral part, and then one for subtracting it from 23 and getting 7. So 1 point for the final answer, 1 point for having the correct integral, 8 to 12 of P of t dt. One thing too you might ask here is, do we, in this particular case, if it's a calculator problem, do we actually have to write out the P to T, or can we just leave this as our answer? You know, again, they want to see how we got what we got, so they're going to need to see some integral, but do we need to actually write in here t cubed minus and all that? No. As long as P of t is clearly defined by the problem, you don't need to rewrite it on your paper. And you can just write P of t. As long as P of t is clearly defined, then you're good to go. Okay. All right. Final part. Part D, it says, according to the model from Part C, at what time were the entries being processed most quickly? So, the time frame, remember, in this problem, looking at Part C, is from 8 to 12. Very important that we recognize that. What are included on this? Endpoints. So if we have a closed interval, okay, I would always suggest using the candidate test, which means that we want to figure out what is our P of 8, that is, and then what is our P of 12. Okay, identify those as candidates, because that very well could be a possibility. Okay. And again, we know that those are possibilities for, again, we're looking for when is, when are they being processed most quickly. And so we know that, again, P is our rate function. Okay, and so if we find the derivative of P, okay, that's going to be, in our case, 3t squared minus 60t plus 298. And so our other candidates here, because remember P is a rate, so if we put in 8, that's going to be the rate at time 8. 12 is going to be the rate at time 12. And we ultimately want to know which one of those is the biggest number. Ultimately, that would be our fastest rate, wouldn't it, when the P is the greatest number. So our other candidates are going to come from this, and again we could solve that with a quadratic formula or by factoring, but again it's just a calculator problem, so if I were you I would graph it and find the intercepts here. So 3x squared minus 60t plus 298. And we can see one of them, but we can't see the other, so I'll move my window over to, say, 15. There's our other two candidates. That's where the derivative of our function equals 0. So if we use our 0 command, get 9.1835034. And the other one, use 0 command again. 10.816497. So those would be the other candidates where P could be a maximum. So if we put those in, 9.1835034, 10.816497, we ultimately want to check and see. Again, it's a closed interval here. We want to see which one of these gives P as the greatest. We know that there's no singular points here because P always has a derivative, so there's no spot where the derivative doesn't exist. So to check it out, I'd probably use my table if I were you. We put our x cubed minus 30x plus 298x minus 976. Yep, got it. There we go. The rest is good. Alright, and if we do our table, I put my table on ask. Got 8, got 12. So those are the rates, and keep in mind these rates we're finding are in hundreds of entries per hour. So we're not doing any at the time 8, the initial time. At midnight, we're cranking them out at 800 per minute. And then if we put our 9.1835034, 5.087. Ultimately, at this point, the right endpoint is winning, right? The biggest one we're looking for. And if we put in our other one, 10.816497, 2.9133, 113 that is. And so since this one is 0, this one is 8, this one is 5.0887, and this one is 2.9113. So who wins? Time 12. So at time 12 at midnight, the entries are being processed at the quickest rate, which is ultimately a rate of 800 entries per hour. Alright, so figuring that out, our point values was to, being able to find these two was worth a point, so if you found those two, that was worth 1. So if you did your derivative, set it equal to 0 and found 2 answers, you got 1 point for that. If you identified your other candidates, which are these two, the endpoints being candidates, you get a point. And then your answer with justification. The justification here, keep in mind, is the candidate test. You've shown all the candidates. Okay. That is the justification. So at time 12, which is your answer, you found that time 12 by getting all 4 candidates, showing which one is the biggest, and you're good to go. That's your extra point. Questions? Alright, so for tomorrow, I want you to work on numbers 4 and 5. So we already did numbers 3 and 6. We'll do those on Wednesday. So 4 and 5 for tomorrow. So you got a few minutes to start working on those.